We want to talk about what we talked about last time. We had discussed making a relationship between the elastic property of a metal wire, okay, 10 kilogram mass or something hanging at the end. We saw the wire stretched by some certain amount. And then what we worked out kind of hastily at the end of the class last time was a relationship. If we were modeling this as a ball of spring model of a solid, then at the microscopic level what we've got is chains of atoms, and many parallel chains of atoms, not just one single thread of atoms, that are connected to this hanging mass. And we're able to think about the behavior of a spring. You have two springs in series. Given the same mass hanging, the stretch would double, right? If you had two springs in parallel, given it hanging from the same mass hanging from both at the same time, the stretch would be half that. And so using that, we were able to come up with a relationship between the overall effective spring stiffness of a wire and the number in, I can't remember, it was number in parallel, not the number in series, I think. Don't quote me on this. Series over parallel. Case of S effective is series over parallel. Was that right? Case of S effective is n parallel over n series times case of S interatomic. Is that right? Is that correct? Everybody check their notes? Yeah, I'm good. Okay. So using that, we were able to then do some dimensional analysis, right? We knew the length of this, and we had already previously worked out what the interatomic spring bond length was, or the size of an atom, essentially the distance between the nuclei of the atom. We can figure out the number in series by looking at the length and the distance, and we can figure out the number in parallel by looking at the cross-sectional area. Okay, so if you imagine this is a cylinder or something, then blow this up essentially. And that's the cross-sectional area, not the surface area, but the snip the wire in half, look at the end, that's the cross-sectional area. Using that and the area d squared of an atom, we were able to work this out. So just a reminder, we found for copper, case of S, interatomic copper, if we worked it out, it turned out to be something like 30 newtons per meter. So we'll hang on to that. And that's a material property. That's a property of the interatomic bond of solid copper. So we can use that, again, the power of sort of connecting macroscopic measurement to microscopic properties, and then using those microscopic properties to explain behaviors of materials. So for example, we say lead, we notice that lead is much softer than aluminum, and can be more easily deformed or pulled into a wire. So what difference between the two materials best explains this? Lead and aluminum atoms have different sizes, they have different masses, or they have different interatomic spring stiffnesses. Okay, clearly answer number 3, right? And almost unanimous, not quite. Interatomic spring stiffness is different. So that explains the stretchiness or the malleability of a material, right? It kind of makes sense. Lead which has the bigger stiffness? Which has the bigger spring stiffness? Lead? Aluminum, right? It's stiffer, so it has a higher spring constant. So, in fact, it turns out if you do the same sort of calculations as we did last time, you'd find that case of S for aluminum is, I think, about 16 newtons per meter. Case of S for lead is something like 5 newtons per meter. Okay? And then we worked it out for copper last time as well, something like 30 newtons per meter. So they're different, and explains the softness, the stretchiness, the elasticity of the materials. But they're not that different, okay? They're not off by many, many orders of magnitude. It's not like copper is 1,000 or 1,000,000 times bigger in terms than lead is. It's just 6 times bigger. Knowing these numbers are kind of ordinary numbers is kind of a good idea, good thing to keep in your mind as you're doing problems and dealing with these types of systems. Okay. Let's look at a different way of talking about the elastic properties of material. If you try to do some research or look something up in a table or online about the elasticity of a metal, they probably wouldn't give you the interatomic spring constant. They'd probably give you some other property of the material, which we're going to call Young's modulus. And let me define 2 things. One I'm going to call the strain. And strain is just the fractional change in length, a fractional stretch of a wire in tension, for example. So that would be the change in length, delta L, divided by the original relaxed length, L sub 0. Okay. Another thing I'll call the stress, which is the tension force at the end of that wire. Per unit area. So that's the force divided by the area. Quantity Young's modulus then is then defined to be capital Y. We get the symbol capital Y, and it is the stress divided by the strain. In other words, capital Y is F over A divided by delta L over L. And that's a useful quantity because, again, it's a property of the material. It doesn't matter what the dimensions of the wire are. It doesn't matter how long it is because we're looking at the length, the change in length per unit length. Okay, so we're dividing out that length. It doesn't matter how thick it is. It doesn't matter what the cross-sectional area is because we are dividing it by the cross-sectional area, F force per unit area. So that's a material property. Okay, and let's actually calculate it for copper based on what we did last time. We said the example last time, we had a copper wire. The original length was 2 meters. We had 10 kilograms hanging from the end, and the stretch, delta L, was 1.51 millimeters, and the cross-sectional area was 1 square millimeter. Okay, so I need to convert that. I need to say this is 1 times 10 to the minus 3 meters quantity squared, or 1 times 10 to the minus 6 meters squared would be the cross-sectional area. So let's calculate Young's modulus for copper. We have the force. Well, what's the tension force going to be in this case? 10 times 9.8, right? We know that if there is gravitational force pulling down on the mass, which is mg, or 10 times 9.8 newtons, then if the momentum isn't changing, it's just hanging there stationary, we know then the net force has got to be equal to 0. If the net force is equal to 0, then the tension force in the wire has to be equal to this. So we know that's going to be 10 times 9.8, or 98 newtons. So we have 98 newtons divided by the area, which is 1 times 10 to the minus 6 meters squared. That quantity, all divided by delta L, which is 1.51 times 10 to the minus 3 meters, divided by 2 meters. So plug that in, and you get Young's modulus for copper. Okay, 1.3 is close enough, times 10 to the 11th. What are the units? What are the units? What are the units of strain? Strain is delta L over L. You have change in length over length. So what happens to the units? They cancel out, right? Strain is a unitless quantity. It's just a pure number, a fraction. So all we're left with is units of newtons per meter squared. Okay, so 1.38 times 10 to the 11th newtons per meter squared. If you look this up in a table or look it up online, you might see that it's listed as 130 capital G PA. What's the prefix capital G for in SI units? Giga, 10 to the 9th, right? So we have 130 times 10 to the 9th, which gives us 1.3 times 10 to the 11th. And a PA, anybody know what that is? Yeah, it's a Pascal. That's a unit of pressure, but it turns out that pressure and stress have the same units, right? It's a force per unit area, so 1 Pascal is 1 newtons per meter squared. So if you run into that notation, that's just what it means, okay? Gigapascals. Okay, so it's a useful quantity for parameterizing the elasticity of material. And it says that since it's a constant, or at least mostly constant, that if we were to plot so we're applying, say for example, applying more and more weight to the end of that wire. So I'm going to plot the stress down here on the x-axis, and I'm going to see what happens to the strain on the y-axis. And so I'm plotting more, or I'm piling more and more weight at the end of the wire, and the strain goes up, but the slope should be a constant, right? And the slope is telling us the relationship between stress and strain. So that's telling us something about Zoom's modulus. And in fact, strain is equal to, what would it be? Strain would be equal to stress divided by y, right? So the slope of this line is what? Is it y? What's the... so it's strain of stress. So strain is equal to slope, right, times the stress. So the slope must be y, right? What am I dividing by y here? But I'm multiplying. But if you write a slope, y is equal to mx, right? And m is the slope. So use the analogy. This has got to be 1 over y. Okay, slope is 1 over y. This plot. All right. So the key point is it looks linear, right? Because it's a constant slope until it doesn't anymore. And the problem is that you can't keep piling the weights on forever, because what eventually is going to happen? It'll break, okay? And in fact, before it breaks, something funny kind of happens. You keep piling weights on, and it keeps stretching a little bit more, and it keeps stretching a little bit more. And then you pile some more weight on. All of a sudden, the strain goes off the charts. It just goes up, way up like that. And what happens is the model basically breaks down. We're modeling this as, again, a ball and spring model. So it's like I'm just hanging all these weights, and I keep stretching all the interatomic bonds more and more, and they just have to be stretched until you reach a point where the atoms sort of start to slide over one another. So you have layers of atoms kind of moving rather than just stretching as you pile more and more weight up. And they say the thing actually yields. Okay, I think engineers sometimes say that this is the elastic regime, and then this is the plastic regime where it yields. Okay, so you got to be a little bit careful. This is an approximation for a specific behavior only in a specific regime or a specific region, and then eventually if you pile too much on, it just breaks. Okay, but it at least gives us sort of the flavor of what's going on over some particular approximation. Questions? Yes?
How do you know when that point is going to roughly occur?
I think it's just a matter of experimentation. I don't know if material scientists can actually predict it, or if there's a particular stress limit that is measured for certain materials where the yielding point actually occurs. So I'm not sure what varies there. I'm not sure if it varies by. I'm sure we'd have to. Let's see. I'm not sure. I think it's another material property. Okay, where the regime change is. But there may be other factors influencing it that depend on the geometry as well, how thick it is or how thin it is. So I'm not quite sure about that. But you can. But I've seen it happen because in fact we'll be doing a lab in a week or two where we will be doing this. We'll be applying weights just to an end of the wire and see if you can measure Young's modulus. And don't do it because you might hurt something if the wire breaks. But if you pile too much on, you actually see it go, and it just doesn't work. This model just doesn't work anymore. Other questions? Okay, let's try maybe a question or two. And let me write the relationship again here so we can see it. So we have Young's modulus is force per unit area divided by change in length over original length. Okay? So given that, you hang 10 kilogram mass from a copper wire, and the wire stretches 8 millimeters. Okay, so clearly this is a different cross-sectional area than the example we looked at before, where the stretch was only 1.5 millimeters, but we'll just use it as an example. So 10 kilograms makes the stretch 8 millimeters. Now you hang the same mass from the second copper wire, whose cross-sectional area is half as large, but the length is the same. Length is the same. What's going to happen? Is the second wire going to stretch half as much, the same, or twice as much? Okay, second wire should stretch twice as much. And you can see that just coming from Young's modulus. We can just reason with the formula here. We have Y being a material property. Okay, so that is a constant. And let me just rearrange this a little bit. We have delta L over L sub 0 being equal to Y times F over A. And in fact, I can even do the delta L over the other side. Right? And then just look at the formula, see what changes, right? The force, is that different? That changed? No, the tension force is the same. We're hanging the same mass. The length is the same, right? Young's modulus should be the same. It's copper. The only thing different here is the area, right? So if the area is now 1/2 of what it was before, then bringing that fraction up, I have then 2 times the change in length as I had before. So it's now stretched by 16 millimeters, right? No trouble there. Let's try one more. Skip that one. Let's go to this one. Same sort of idea. You hang a 10 kilogram mass from the copper wire. The wire stretches by 8 millimeters. And now you hang the same mass from a second copper wire, which is twice as long, but has the same diameter. So what's going to happen in this case? Okay, a little less unanimous this time. Well, let's see. We're still trying to figure out what happens to delta L, right? So we rearrange it so that it is on this side of the equation. Delta L is over here. What changes? Did Young's modulus change? No. Did the tension force change? No. Did the cross-sectional area change? No. Did the original length change? Yeah. So now the original length has gone up by a factor of 2. So if I multiply this, replace L with 2L, what happens to the length, or the change in length? It goes up by a factor of 2. Okay? This is just like what? What did we do last time? This is just like 2 springs in series, right? If I have, let me see if I can actually do this. So here's the relaxed length of the spring, and if I hang this mass from the spring, it stretches that much, right? And here's another spring which has about the same relaxed length. I connect them in series here. Then that's now stretching that spring as well. Okay, so they're both stretched by the same amount, but if I just double the length, I've got double the stretch. So it's just like having, because we're just modeling like it springs in series, so it's just behaving exactly the same way. Okay? So we have 3 is 4. We okay? Questions? All right. Yes, question. Yeah. It was 3. It was 3. Because we're looking at the overall stretch of the whole length of the wire.